So far we have gone through 3 examples about the design of columns subjected to biaxial bending. The details and the specifications are similar, except that the conditions of the columns differs. In question L, we deal with the short column subjected to biaxial bending. As for the question M, we deal with the slender and braced column subjected to biaxial bending. And then in the questions N, we deal with the slender and unbraced column subjected to biaxial bending. For more details, if you wish to know step-by-step calculations, you may refer to our previous videos. In these videos, we're going to compare the design outcome of these 3 questions and state our findings based on the calculated results. Without further ado, let us get started. We deal with the short column first. The column is subjected to the biaxial bending, where we have the MED calculated as given here. Since there are moments acting in both axes, we need to calculate the MED for both axes. As for the slender braced column and the slender and unbraced column, we also do the same to determine the MED. Having the same set of moments acting onto the column, but the calculated MED differs by the column type. This is mainly due to the equation used to determine the MED. Short columns only deals with the first order moment, where the moment acting onto the column will need to be added up with the moment due to imperfection. Whereas for the slender column, you will need to incorporate the second order moment. In the braced structure, the second order moment may or may not influence the MED. However, for the unbraced structures, the second order moment is definitely a concern in the column design. This leads to the calculations for the MED differs by the column type. Now, if you refer to the MED calculated, obviously the slender and unbraced column, it will be the most critical. Whereas the slender and braced column, it will be more critical than the short column, but less critical than the slender and unbraced column. Having the MED calculated, we might not be able to use this value straight in the design of the reinforcement, because we will need to check whether we need to take into account the effects of the biaxial bending. If we need to consider those, that means we need to determine which axis it will be more critical, and then work out the new MED on the more critical axis, taking into the considerations of the effects due to another axis. In order to determine whether the biaxial bending needs to be considered, we are looking into these 4 components. These 2 must be fulfilled, and either of these 2 must be fulfilled. Otherwise, biaxial bending will be required. In this case, all 3 columns require the checking of the biaxial bending. Knowing this needs to be considered, our next step it will be to determine the new MED due to the influence of the biaxial bending. First, we need to determine which directions it will be more critical. This is by getting the ratio of the moment against its effective depth. All 3 of them have the minor axis to be more critical than the major axis. You see, this ratio varies by the type of the column. This is mainly due to different MED as acquired from the formulas to get MED. Ultimately, All these three columns have the same findings, where the minor axis is more critical. Knowing the minor axis is more critical, you will need to determine the M prime ED Y. Taking the moment acting onto the minor axis plus the influence due to the other axis. This leads to a significant increase in terms of the moment that later you're going to use to design for the reinforcement. Again, you will see that slender unbraced column will still be the most critical one. And then, based on the M prime EDY, you refers to the column design chart and work out the AS required. This will be the first round where you're going to propose the amount of reinforcement. Later, you will going to check again for the biaxial bending using this equation. Based on the column design chart, these are the AS required. Therefore, you're going to propose the relevant reinforcement, which for the short and biaxial bending, you will need 4H16 plus 2H12. As for the slender braced column and slender unbraced column, the amount of reinforcement bar provided are 6H20 as far as the minor axis is concerned. Bear in mind that the dimensions of the column vary slightly. The size of the column for the slender unbraced biaxial bending column is slightly larger than the two. Later, during the checking for the slender and braced column, you realize that this section is too small. Coming back to the amount of reinforcement bar provided, since you are designing the AS provided in the minor axis, you will have to imagine how the reinforcement bars are to be provided. For H16, it will be this, plus 2H12. If you are talking about the minor axis, you will have 6 units of reinforcement bar to be effective. However, if you're considering from the major axis, the 2H12 here is at the neutral axis. This 2 bar will not be effective for the major axis. That's why, as far as the major axis is concerned, only 4H16 is provided. Same principles goes to the slender and braced column. You are providing 6 units of H20 steel bar. 2 of them are not functional in the major axis. That's why effectively you have 4H20. Same concept goes to the unbraced slender column. Once you have the reinforcement bar proposed, you will need to check the minimum and maximum bar area. It seems that the columns is quite heavily reinforced. The maximum bar area might be a critical issue. For the short column, it passed, and then you check for the biaxial bending using this equation. Remember, while checking for the biaxial bending, when you use the MED in the major and the minor axis, you will need to keep the moment due to imperfections on the unfavorable axis, which in this case, the unfavorable axis, it will be in the minor axis. You will use the MED for the minor axis since it is more critical, but the MED for the major axis, you will have to remove the effects of the moment due to imperfections. That means the MED for the major axis, it will be slightly smaller than this. And then you do the biaxial checking, you realize that the short column passes. That means you can keep with the design of 4H16 plus 2H12. As for the slender and braced column, the proposed design it will be 6H20. However, when you check for the maximum bar limit, it exceeded 4%. It means that the column sections is not large enough to accommodate the reinforcement bar. You will expect the column fails in a brittle manner, and your solution here it would be to redesign this section. Since you know that the column is going to fail, you don't have to check for the biaxial bending anymore. It is no point even though this one passed, since you are not allowed to have the reinforcement bar exceeding the maximum bar area. Ultimately, this layout of reinforcement bar cannot be used, and you need to redesign the section. As for the slender and unbraced column, which is subjected to biaxial bending, the proposed amount of reinforcement bar in the minor axis it will be 6H20. Due to the layout of the reinforcement, which looks something like this, 2 of the H20 reinforcement falls at the neutral axis of the major axis. That gives you only 4H20 effective in the major axis. Due to slightly larger cross-sectional areas, this amount of reinforcement bar was found not exceeding the maximum bar area. Up to this stage, the proposed reinforcement bar seems to be acceptable. However, you will need to go through another level of checking in terms of the biaxial bending, which is this one. Based on the amount of reinforcement bar provided, 6H20 in the minor axis and 4H20 in the major axis, you get the moment resistance for the major axis and the minor axis. Calculate the NED per NRD ratio, you get the factor A, and then you calculate the MED for the major and the minor axis. In this case, you know that the minor axis it will be more critical. That means the calculated MED for the minor axis it shall remain the same. However, you will need to remove the moment due to the imperfections from the major axis and then substitute into the equation. The equation ends up to be more than 1.0. That means the initially proposed amount of reinforcement bar is insufficient. In order to make it sufficient, 2 more reinforcement bar is provided in the major axis. Instead of having the reinforcement bar arranged in this manner, now you will have the reinforcement bar arranged in this manner. In the minor axis, there will be 6 reinforcement bar effective. As in the major axis, there will also be 6 reinforcement bar to be effective. Based on the amount of reinforcement bar effective, you recalculate the MRD for the major and the minor axis and then test the number. See if it is less than 1.0. The calculated result shows that the newly proposed amount of reinforcement bar passed the biaxial bending check. Ultimately, this is going to lead to a total of 8H20. Since the column is quite heavily reinforced, we will need to check the maximum bar area based on the newly proposed reinforcement, comprising 8H20 in the sections of 175 times 300. The result shows that the maximum bar areas has been exceeded. Although the proposed 8H20 in the sections passed the biaxial bending check, but the amount of reinforcement bar has exceeded the limit. Therefore, such a design cannot be applied, and we will need to increase the size of the section, preventing the amount of reinforcement bar exceeding the maximum bar limits. Redesigning the sections, that means you have to go through the calculation steps once again until all the checking requirement, particularly the biaxial bending, passes, and also make sure the maximum bar area is not exceeded. This is about the calculated result from the 3 examples, which give us some interesting findings, such as the proposed sections 150 times 300 is adequate for the short biaxial bending column, but this sections is not adequate for the slender biaxial column, regardless the column is braced or unbraced. This means that designing a short column with the moment acting in both axes, it will be less critical than designing a slender column. You also see that the amount of reinforcement bar required increases from the short columns to the slender column. Also, based on the result, both the slender columns in the proposed size of the column fails in the maximum bar area. That means these 2 columns fails and the proposed sections is inadequate. In order to ensure the stability of these 2 columns, we will need to enlarge the column section. Next finding, you see that for the start, we will need to determine the design moment both in the major and the minor axis, since we know that there will be moment acting in both axes. And the design moments increases from short to slender column. Among the slender columns, unbraced column, it will be more critical, as can be seen by the magnitude of the design moment, both in the major and the minor axis. Next is the importance of the aspect ratio of the column. The meaning of the aspect ratio is the relative comparisons between the dimensions of the column in the major axis and the minor axis. Now, if the major axis is significantly greater than the minor axis, that means the critical site most likely will end up to be in the minor axis. This is what it means by the aspect ratios of the column shall determine the critical site of the column subjected to biaxial bending. Now, if you look at the calculations, the method used to determine the critical site, it will be on basis of the ratio in terms of the moment versus the effective depth. That means the moment is another aspect that can influence which side will be more critical. Now, in the case that the minor axis will have significantly larger moment in relative to the major axis, this may also lead to the minor axis to be more critical. We might not be able to immediately identify which side it would be more critical in the first glance, but we have proper calculation step for us to confirm which side it would be more critical. Next, due to the effects of the biaxial bending, we see an increment in terms of the design moment between the individual axes and those after considering the effects of the biaxial bending. All 3 columns here are critical in the minor axis after considering for the effects of the biaxial bending. The design moment MED increases, and the increment can be quite significant. That means that if we are designing the reinforcement based on the individual axis without considering the effects of the biaxial bending, this might underestimate the amount of reinforcement bar required in the column. Next, we will need to be careful in terms of the effective reinforcement, functional within the major and the minor axis. You see, when we calculate the AS required, the AS required was proposed based on the MED of the column in the more critical axis. In this case, the minor axis is more critical. Now, when you provide the reinforcement bar on basis of the minor axis, the same amount of reinforcement bar might not be effective in the major axis. Therefore, it is important for you to sketch the reinforcement and then to see the amount of reinforcement bar effective in the non-critical axis. In this case, we observe that we propose 6 units of reinforcement bar in the minor axis. It eventually ends up to be only 4 reinforcement bar effective to the major axis. This you have to be careful. If we wrongly identify the effective amount of reinforcement bar, this may lead to us overestimating the moment resistance of the non-critical axis. As a result, we will have calculated wrongly in terms of the biaxial bending checking, which through the calculations it may seem pass, but actually the member failed. This reflects the importance of us to identify the effective reinforcement to the individual axis of the column. Another interesting finding is designing the reinforcement based on the M' EDY does not necessarily passes the biaxial bending check. Remember, in the design of the biaxial bending, knowing the biaxial bending needs to be performed, we first go through these calculation steps in order to calculate the MED, taking into the account of the effects of the other axis. Use the calculated MED in the design chart and come up with the AS required. Our calculation steps cannot stop here. This step is meant for us to work out a reasonable AS. And these equations in fact are not given in Eurocode. This method here is given in British Standard at 110. Passing this cannot be taken as passing the design for the biaxial bending column. We will need to go through the process of checking the biaxial bending of the column as per the requirements of the Eurocode. As demonstrated by question N, for the slender unbraced biaxial bending, the initially proposed amount of reinforcement bar passes the British standards. However, when it comes to the checking due to the Eurocode, it fails. This leads to revisions or increment of amount of reinforcement bar from 6H20 to 8H20. Only then the requirements by the Eurocode passes. However, having the reinforcement proposed, make sure we do checking in terms of the maximum bar areas, which in this case, even though you pass both methods, but the required amount of reinforcement bar has already exceeded the maximum bar area. This gives you an idea that the column sections is too small, which you need to increase the section size. With that, by comparing these 3 examples here, we gain in-depth understanding regarding the design of column subjected to biaxial bending. Up to now, we have done a series of examples related to the column, dealing with various types of column subjected to uniaxial moment, including the short column, braced slender column, unbraced slender column, moment acting in the major axis only, moment acting in the minor axis only, and also moment acting in both axes. You may compare the calculation steps in order to observe their patterns. Although the steps seems to be changed quite significantly, but they're actually following certain simple rules. You can try to find out those rules by yourself. You're going to find it quite interesting and satisfying to find those rules. Understanding those rules, now you will have no difficulty designing any type of columns: braced, unbraced, short, slender, moment acting in the major axis, moment acting in the minor axis, and also moment acting in both axes. You should be able to deal with that. With that, all the best and good luck.